In this lesson, you will learn how to calculate the probability of independent events, as well as determine if events are independent. So first of all, independent events are two or more events are independent if one does not affect the outcome of the other. So two or more events are independent if one does not affect the outcome of the other. So we have these events that we are determining if they're independent or dependent. So we have a number cube landing on a 3, so that's just a basic number cube. And a red card being selected from a deck of cards. So here, a deck of cards. If we wanted to select a red card, got them. So from this deck of cards, selecting a red, okay? So with those probabilities, would they affect each other? If I rolled this numbered cube and I pulled a card from the deck of cards, those probabilities would not affect one another, so they would be independent. It would not matter what I rolled first. Once I go to select a card out of the deck, it could be red or black. It didn't matter what the first probability was. So that's where they're going to be independent. So for our next one, drawing a blue chip, not replacing it, and then drawing a yellow chip. So if we have a bag or a box of chips, if we reached in and pulled out a chip, if we did not put it back in there, it changes the probability because I don't have the same amount of chips to select from. When I first went in and pulled out a chip, I had however many in there, and now I have a different probability to get that next chip. So it is changing, and it does make it dependent. So if events are going to be independent, then the probability of A, so the probability of getting that 3 on the number cube, multiplied with the probability of B, so like for selecting a red card, when you multiply those together, it should be the probability of A intersection with B. Remember, this symbol means and, that's the intersection. So if the probability of A times the probability of B equals the probability of their intersection, then they are going to be independent events. So let's see if we can determine if these events are going to be independent. We've already got calculated for us the probability of A, so maybe the chances of getting a green is 4 out of 7, and the probability of rolling a number less than 3 is 2 out of 5. So we've already calculated probability, and then the intersection has already been given. So we can determine if these are independent by multiplying the two probabilities together. So let's take 4/7 and multiply it with the 2/5. Well, 4 times 2 is 8. 7 times 5 is 35. That does not reduce. So we notice those are not equal. Not equal. Yeah, we can just say They're not equal, so they would not be independent. The multiplication of those probabilities would have to equal their intersection, and it does not. Let's look at our next one. So 1/3 times 3/5. If I multiply, 3 times 1 is 3. 3 times 5 is 15. Notice those are equal, so we will say that these are independent events. So probability of A, that happened 1/3. Probability of B, that happened 3/5. Whatever these events were, they were independent, and the intersection is 3/15. So one event did not affect the other, where in the previous example, they were not independent. Something happened and caused these events to affect each other. So let's look at some examples where we're actually going to be calculating some probability. We have a 20-sided die, so a D20. So it has 20 sides, which include the numbers 1 through 20. So that 20-sided die is rolled and a spinner is being spun. So this is our spinner. We want to know the probability of rolling a 7 and spinning a number less than 3. Well, those are independent events. So because they will not affect one another, we will be able to multiply together their probabilities. So the probability of rolling a 7, well, there's only one 7 out of the 20 on this number cube. The chances of getting a 7, that's one time out of the 20. We can multiply that together with our probability of spinning a number less than 3. So over here on our spinner, a number less than 3, well, we have this 2 and 1, so there's 2 of them out of there's 6 sections, so 2 out of 6, and we can multiply these together. So 1 times 2, 2 times 6, 120, and so we can multiply together and then reduce our fraction. So 2 out of 120, if you hit math, fraction, that will reduce it for you. Let me get it so you can see. There we go. So with math fraction, it reduces it for you. And then you can hit math decimal to round it to the nearest hundredths. That'd be 2 decimal places, so it would be 0.2. Because the number behind that 1, the 6, makes it round up, so 0.2. And then that percent would be, if we need to multiply that times 100, or just move the decimal, it is 2%. So the chances of this happening are pretty slim. Being able to roll a 7 and spin a number less than 3, to be able to do that, you have a 2% chance. Let's look at our next example. This time we want to roll an even number. So on a D20, there will be 10 even numbers out of the 20, or you could say 1/2. And we want to spin a prime number. So 2, 3, and 5 are all primes. Remember, 1 is neither prime nor composite. And 4 and 6 are both composite numbers because they have factors more than just 1 in itself. So 2, 3, and 5 are prime because they have the factors 1 in itself. So there's 3 out of those 6 sections, or again 1/2, and we can multiply those together. So 10 times 3 gives us 30. 20 times 6 gives us 120. And we can reduce our fraction. So go 30 over 120, hit math fraction, and it reduces it for you. And then you can do math decimal to change it to a decimal. Once you have that decimal, you can say times 100 to get the percent. So it's 25%, or if you know to move the decimal, you can move the decimal 2 places. Just be careful on which direction you should be moving your decimal. So it is 25% chance that you can roll an even number and spin a prime number. You have a 25% chance, so a little more likely than our previous example. Let's look at now example number 7. So in a bag there are 3 yellow chips. So here, 3 yellow chips. We have 4 red chips, 2 blue chips, and 1 green. So here is what we're working with for this probability. This is our universal set for our problem. So once a chip is selected, it is returned to the bag. That way it will make it an independent event. If we remove that chip, it would then cause it to be dependent, and it would change the probability of that next event occurring. So first of all, we got to know how many total chips we have. So if we add 3 plus 4 plus 2 plus 1, that gives us 10 total chips. We do need to know that total number when we're calculating our probability. So we first want to know the probability of a red. So there were 4 out of the 10. And because these are going to be independent, because I've selected that red chip, I returned it before I ever select again, we're going to multiply. We still have 4 out of the 10. So 4 times 4, 10 times 10, and then we can reduce that fraction. So 16 out of 100 gives us 4 out of 25. That changed to a decimal gives us 0.16. So that makes it 16%. So we're going to select a red, put it back in, select a red. We have a 16% chance of being able to do that. Let's look at this probability. We want a probability of not getting a blue. Remember, this means complement, so not getting that item, that element. And then we want to replace that and then not get yellow. So if we look at our chips here, if we want not blue, well, these 2 are blue. The chances of not getting blue would be all these other colors. So that would be 8 out of the 10. Because there were 2 blue, we know that 8 of the other ones are not blue. And then if we want not yellow, well, we have 3 yellow, so that would mean that there's 7 that are not yellow. If we have those 3 that are yellow, you can add up these others that are not yellow, and we would multiply together those probabilities. So 8 tenths, we're going to multiply with 7 tenths. Go ahead and hit math fraction. So our fraction is 14 over 25. If we do math decimal, we get 0.56, so that's a 56% chance. And we want to know the probability of not getting a blue. So of our options here, probability of not getting a blue, putting it back in, then not getting a yellow, we have a 56% chance of that probability.